87% of all machine learning projects never make it to production. The model gets built, it scores high accuracy in testing, someone presents a slide deck to management, and then nothing happens. It goes to the Jupyter graveyard. It sits in a notebook on a local machine, completely detached from the daily operations of the business it was supposed to help. Getting out of that graveyard is straightforward if you are building a supervised learning model. You input a new customer record, and the model outputs a clear prediction, like a yes or no on whether they will cancel their subscription. Unsupervised models operate differently. They do not predict specific answers. Instead, they sift through mountains of unlabeled data to discover hidden structures and abstract patterns. Because they don't produce a simple true or false output, figuring out how to actually deploy them confuses even experienced analysts. To put an unsupervised model into production, you have to stop thinking about the algorithm itself. Instead, you extract the mathematical artifacts left behind by those patterns and use those to drive automated decisions. We can see how this works by looking at 3 real-world blueprints. A customer opens their mobile banking app. Before the home screen even fully loads, the bank system has categorized them as a digital-first saver and queued up a targeted push notification for a high-yield account. Behind the scenes, the bank used a K-means algorithm. This algorithm processed thousands of historical account balances, transaction frequencies, and app logins to group similar financial behaviors together into distinct segments. This 3D plot shows behavioral clusters. The algorithm calculates a mathematical center, creating an illuminated centroid node. When a customer opens their app, the system places their new data here, calculating the spatial distance to each node and locking on to the closest one. This real-time deployment requires very little computing power. The heavy lifting is done. You are only executing a basic distance calculation formula, which can be run natively inside a spreadsheet. The deployed clustering model is simply a spatial distance calculator. It maps new data to historical averages to trigger targeted marketing actions without human intervention. Imagine a shopper adding a team jersey to their online shopping cart. The moment the item registers, the site automatically generates a 10% discount offer for a matching cap. To set up that interaction, the retailer took millions of historical point-of-sale receipts and processed them through an a priori algorithm. The algorithm scans every basket to find hidden purchasing patterns. Look at this network web of items. The algorithm evaluates thousands of pairings, assigning a confidence score to measure link strength. To deploy, you throw away the algorithm, filter the results for the highest scoring links, and extract them into a 2-column list. A product manager can then take this structured list and upload it directly into their e-commerce platform. The platform reads the rows to configure automatic promotional bundles whenever a specific item hits a cart. For market basket analysis, the lookup table itself is the deployed model. You turn abstract purchase patterns into hard-coded rules that drive immediate revenue. A traveler swipes their credit card to buy gas at 2 in the morning in a new zip code. Instantly, they receive a fraud alert text, and the transaction is paused. To build this shield, the credit card company trained an isolation forest algorithm on massive historical logs. The algorithm learns the precise parameters of what constitutes normal spending behavior for each account. Here, a dense cluster represents normal transactions. The training phase extracts a single threshold multiplier, creating a rigid mathematical boundary around normal activity. The live system evaluates new transactions by checking a single condition. Does the new data fall outside this extracted boundary? Because it is just a threshold rule, it deploys as a highly efficient microservice. The system evaluates these simple logical statements in milliseconds, flagging anomalies for human review. Anomaly deployment weaponizes a static boundary threshold. It protects live, high-speed systems by applying historical context to new events without constant real-time training. This split screen shows the 3 extracted components side by side: the centroid distance formula, the association lookup table, the anomaly threshold boundary. Many projects stall because teams attempt to wire the heavy, complex algorithm directly into their live infrastructure. This creates a technical mismatch that often forces a model to remain on a laptop as a science project rather than a tool. The unifying blueprint for unsupervised learning is clear. You train the heavy algorithm offline on historical data, but you deploy only the extracted mathematical artifact online. Whether that artifact lives in a sophisticated cloud microservice or an everyday Excel spreadsheet, extracting it is how theoretical models survive in the wild. A model only becomes useful when it influences a real-world business decision. Accuracy in a notebook is just the beginning. The real goal is to have those results scoring customers and triggering actions every single night.